Welcome back. This is part 2 of the secure coding presentation, a continuation of the part 1 slides that I hope you had an opportunity to have already watched. Thank you for joining us. We'll start part 2 by looking at the very basic but important 10 core coding standards with C++ examples. Now, the goal of this presentation is not to teach you how to code, but to point out what secure coding practices ought to include and how they need to be listed in a security policy and guidelines document for all to observe and adhere to in an organization. The main objective to having this document is to ensure robust, secure, and maintainable code. Any programming languages, whether it's C, C++, Python, C#, Ruby on Rails, what have you, by adhering to best practices and standards. There are 10 core coding standards by category listed here as a start for your security policies and guidelines creation or updates. We shall look at some C++ code snippet for compliant and non-compliant versions for comparison. First, you will see the non-compliant version and then the compliant version for comparison. There are other very relevant and necessary coding standards that were not included here, of course. You can add them later as you're improving your security posture in terms of having more and more items and updated policies and guidelines. There is a threat level table for each coding standard. Threat level table is a critical component of our software development policy and guidelines designed to categorize and prioritize potential vulnerabilities within your code. There are several essential functions that this table serves. Risk management. The table helps developers and security professionals to quickly identify which types of coding issues pose the greatest risk to the application. By understanding the threat levels, teams can focus their efforts on mitigating the most dangerous vulnerabilities first. It helps you to prioritize what kind of security measures you put in first, how much time and effort you want to put in based on the severity level, impact level, and threat level, so that you can allocate your resources efficiently and addressing the most critical vulnerabilities effectively. You want to integrate automation tools to automate the detection and fixing of these vulnerable code areas, the coding areas that we're going to look at the 10 of them here. This table also serves as an educational resource, excuse me, raising awareness among developers about the various types of security threats and their implications. It encourages continuous learning and improvement in secure coding techniques. Furthermore, this is for supporting compliance and auditing. By providing a structured approach to identifying and addressing vulnerabilities, the threat level table aids in meeting industry standards and regulatory requirements. It ensures that security measures are in place to protect sensitive data and maintain compliance. So let's jump right into the coding standards. Number 1, input data type validation. You're looking at a little bit of a code snippet on a non-compliant version of how input data type validation is not done right. This code here assumes that the user will enter a valid integer. Now, while I'm describing it, you can look at the code. It's a very simple code segment here. If the user enters non-numeric input, the std::cin fail check will detect this error. But the code does not properly handle the invalid input. Instead, it simply prints an error message and exits the program. This code here is very simple, very straightforward. It compiles, it links, it runs. But it's not robust. It is also likely not doing what you intended it to do. A more robust version looks like this. This code here uses std : get line function to read the user's input as a string. When you enter something on the console, it comes through as a string. It then attempts to convert the string to an integer using std : stoi, stands for string to integer function, which throws specific exceptions if the input is invalid or out of range. This code here correctly handles these exceptions, printing appropriate error messages and returning a non-zero exit code to indicate the failure. So here I pointed out the key differences between the non-compliant and the compliant version, and you can see how much more robust this version is. Threat level table for input data type validation. Severity is high, likelihood is high, remediation cost, which is how much does it take to fix this problem, is medium, priority is high, and threat level is 1. Level 1 is the highest threat level. The automation table underneath it is listing 4 different automation tools that can do this input validation checks: Fortify, SonarQube, Cofferty, and Checkmarks. I hope I'm pronouncing all of the names correctly. They are all capable of doing input validation, which is to ensure proper validation of input data to prevent common vulnerabilities. Coding standard number 2, data value validation. So we just did data type validation. This is data value validation. The code here is also super straightforward. It assumes that the user will enter a non-negative integer for their age. If the user enters a negative value, the code will simply print an error message and exit the program. This approach is not robust at all, as it does not handle other types of invalid input values, such as a non-integer value, or if a value is gigantic that an integer bucket cannot even hold. So what is a better version? A better version here looks like this. This code here uses a while loop to repeatedly prompt the user for input until a valid value is entered. It first checks if the input can be successfully read into the age variable using the std's : cin, pushing out to the age variable expression. If the input is valid, that is not zero and not an integer, if it's invalid, that is not zero and not an integer, the code clears the input stream and ignores the rest of the line, then prompts the user to try again. After successfully reading the input, the code checks if the value of age is negative or if it's 0. If it is, the code prints an error message and continues the loop, prompting the user to enter a non-negative value. Once a valid input is received, the loop terminates and the program proceeds to print the user's age. You can see here it also checks to see not only if the age value is not 0 or negative, it also checks to see if the number is bigger than an integer value can hold. That's what makes this code much more robust. So, after listening to all the key differences between the non-compliant and compliant version, you can see clearly that this is the version that we should adhere to, making sure that it has all the bells and whistles that will help us prevent vulnerabilities or undefined behaviors. The threat level table here for this particular standard: severity is medium, likelihood medium, remediation cost low, priority medium, and its threat level is 2. For automation, input validator, data sanitizer, input verifier, form validator, these are commercial tools. Some of them are even free. You can use to check values, whether you have valid input values coming into your program. value checker, value validation, comprehensive validation, excuse me, range checker. These are all applicable to this particular coding standard. All right, number 3, string correctness. Now, when we're talking about how to handle strings, there are so many string functions that you can choose from. A lot of them are not safe for you to use. For example, strings that do not check length, copying a string, come right off the top of my head. Copying a string from one variable to another and you don't specify a length for checking, those functions are not safe. So when you do strings, when you work with strings, make sure you're calling safe string functions versus those that are not safe. Now, I can cite at least 2-3 dozen examples, but here's a very simple one. This code here, with the line std_cin pushing the input to this variable called name, will only read the first word of the user's input, ignoring any additional words. This is obviously not what you want. If you're talking about a name, it could easily have the first name and last name 2 words, first name, middle name, and last name 3 words. And for people who are from European countries, easily you can have way more than three separate words. So this can lead to unexpected behavior if the user enters a name with multiple words and you only get in the first word and there's a white space after that, you ignore everything else afterwards. This is obviously not what you want. A better version is to use getLine. Use std::getLine to read the entire line of input, including any spaces, and store it in the name, in the variable that's called name. This ensures that the user's full name is captured correctly, even if it contains multiple words. Additionally, to handle cases where the user enters invalid input, for example, a non-alphabetic characters, you can add input validation. So this compliant version uses a loop also to repeatedly prompt the user for input until a valid all alphabetic name is entered. The code uses std_is_alpha to make sure that did you enter an alphabet or not, right? So is_alpha to tells you is a boolean to tell you true or false. This is an alphabet letter, and to use that, you need to include the CC type header to check if each character in the input is a letter. If any non-alphabetic character is found, the user is asked to try again. So clearly, this is a much robust version. Thread level table. Now this is thread level 1, because if you're not reading everything from the input, it's not even the thread. It's not functioning correctly as you intended. But the severity is high, likelihood is high, remediation cost medium, priority high, and threat level is 1. So that gives you an idea that if you are doing something like this, make sure that your string manipulation, string handling is robust. 4 different tools, automation tools you can use to do string handling: Fortify, CPP check, Clockwork, and Coverty. They all do string manipulation, string handling, string operations to make sure that it can detect unsafe string handling practices to prevent buffer overflows and other vulnerabilities. Coding standard number 4, SQL injection. For those of you who do a lot of SQL query programming, this is elementary, but it is still required to put it on your document, on your security policies and guidelines. Now, this particular non-compliant code, you can look at the code while I describe it. The user input is directly concatenated into the SQL query. This makes the application vulnerable to SQL injection attacks, where an attacker could inject malicious SQL code into the input to gain unauthorized access or perform other malicious actions. Never, well, let's look at this select statement here. Select asterisk from users where username equals something and password equals something. Now, if this statement is concatenated with a string that says or 1 equals 1, what will it do? The portion that says or 1 equals 1, the 1 equals 1 is always true, right? So if that part is always true, you are opening up a door for people to access your whole SQL database. Meaning, or select all the users from the database and show them to me. And because the second part of my statement is true, 1 equals 1, 2 equals 2, or what have you, is always true. So the moral of the story is, do not concatenate SQL queries just like that, like into a string, because that is extremely risky. What is a better version? The better version is to use prepared statements to execute any SQL query. Prepared statements separate the SQL query from the user input, preventing the user input from being interpreted as part of the SQL code. This effectively mitigates the risk of SQL injection attacks. So the key steps in the compliant code are, let me point them out. Prepare the SQL statement using SQLite 3_prepare_v2, that is a function, leaving placeholders for the user input. You then bind the user input to the placeholders using SQLite 3_bind_text. You are essentially binding your username and password into that text. And then you execute the prepared statement using SQLite 3_step. Lastly is to finalize the prepared statement using SQLite 3_finalize. These are the steps that you can really cut and paste and use it to make sure that it works as it intended it to be. By using prepared statements the way I just described to you, the compliant code ensures that the user input is treated as data, not as part of the SQL code, making it much more secure against SQL injection attacks. The threat level table severity is critical. This is critical. Why? Because if you are concatenating an SQL statement incorrectly, you are opening up a big hole for users to go and access your whole database, get all the sensitive data out and use however way they want to and create absolute havoc and could cause a lot of damage. So severity here is critical. Likelihood high. Remediation cost medium. If you follow those steps and do the right way, you're fine. Priority high and level threat is 1, the highest level. There are 5 automation tools I can recommend for you to use. They all check for SQL injection. SQL Map, Fortify, SonarQube, AppScan, and Checkmarks. They all help you to detect potential SQL injection vulnerabilities in your code. They automatically do this. So again, automation is key to a lot of these coding standards. Next is memory protection. Now I'm citing very simple things, but it's applicable to more complicated code base. Usually we're talking about thousands of lines of code. And for debugging memory issues, it could be so time consuming and could be intense and time consuming and high effort, and then still you don't know where it happens. Even though there are a lot of very good debuggers now these days that could help you. But simplicity is beauty, so let's take a look at it. This is really just telling you this 2 lines of code fails to manage memory properly because it's not cleaning the newly allocated memory after it's allocated, and it's leading to memory leaks. You are using the new keyword to allocate 100 integers to an integer array called ARR, and then you did not delete it. Now, there are other higher level languages that would take care of cleaning up resources that are no longer in use, but you always want to bear in mind that the programming language that you're using is capable of doing that. In C and C++ and a few others, they don't automatically clean up after you. So this is always good to pay attention to make sure that indeed, do I need to clean up? Am I using the right memory functions, etc.? Now, this is a much better way to do it. This code here uses smart pointer. Now, C++ has smart pointers. There could be other equivalent features in other programming languages. But the concept here is, if you use smart pointers, they will manage memory properly for you to prevent memory leaks. You don't have to delete the allocated memory because it will know how to deallocate it and release the resources for you after it's no longer in use or if it is out of scope. So here, the smart pointer is unique pointer, std : unique pointer, and allocating a new integer array of 100 instances. The memory is managed properly by smart pointer, so you don't have to worry about releasing these resources. Now, for smart pointers, of course, there's shared pointers. There are weak pointers. You can look them up and use them as to which one you need in your specific applications. Smart pointers are an essential feature in C++ that can help manage dynamically allocated memory automatically, ensuring that memory is properly released when it is no longer needed. This really helps prevent memory leaks and dangling pointers, which are common issues in manual memory management. Okay, so the severity here is medium, likelihood medium, remediation cost low, priority medium, and threat level 2. There are 4 tools that help with memory leaks. The first one is Address Sanitizer, ASAN. Valgrind is another one. Planck Static Analyzer also, and PVC Studio. They all do memory leaks checking, memory management, and help you to discover memory issues. All right, we're moving ahead. Coding standard number 6. Use assertions properly. This code here is so simple, right? We encountered this from day one. We all know we should not divide by 0 because that will cause either program abort or undefined behavior, but usually program abort. This code here fails to use assertions to check for invariance and assumptions. You are assuming B is not 0. So what if B is 0? Well, if B is 0, then the program aborts. Is that what you want? If not, the better way to do it is to assert. Put an assert statement there. Here it says assert B, which is the divisor, is not 0. And if it is a 0, you will display an error. This is likely a custom assert statement. Check with division by 0. If it is 0, you display a message saying divisor cannot be 0. And the program ends there. It's not an abort, right? So otherwise, you just go ahead with the division. So this is the right use of an assertion, even though in the most basic of scenarios where you need to use it. So So before we move on to the threat level table, I want to point out that if you don't already know, we have two different kinds of assertions. One is the basic native C++ assertions, and the other is the Google test assertions. So very quickly, let's take a look at the standard assertions, which is the native built-in C++ assertion. Usually you include assert.h as the header file, and then you do assert. There are two types of assertions. One is called static assert. A static assert is compile time assertions. It won't even link and allow you to run it properly if this static assert fails. Runtime assertions assert when during runtime. For example, here, the static assert at compile time will assert if the size of an integer is not equal to 4 bytes. So if you're running on an operating system that an integer, a size of an integer is not 4, you want to know about it before you continue, right? So at compile time, this will stop you from going ahead because this will assert if the operating system have an integer size and the value is not 4. Runtime assertion is it will be done at runtime. Here it asserts that the pointer is not equal to null. So at runtime, if the pointer is null, it asserts. So this is the native C++. What about the Google test assertions, which a lot of people uses these days? They are macros, actually. You would include gtest.h. So for example, here, test is a macro, assert gt greater than is a macro, and expect eq is a macro. So in Google test, you have this test unit, and assert 10 is greater than 0. If this is true, that is, assert that 10 is greater than 0, it will assert. But for expect, it's a bit different. And here, if you say expect equal 5 equals to 5, one is fatal assertion and the other is non-fatal. When you use assert, program will stop, will abort if the value is not greater than 0. Right? If this is not greater than 0, then the program will abort. Now, if you want to use expect, the program will show you an error if this value if the value is greater than 0, but the program will not stop. So this is the difference, fatal assertion and non-fatal assertion. Okay, let's go back then to the threat level table. For assertions, severity is medium, likelihood medium, remediation cost low, priority medium, and level 2. There are 5 different automation tools that does assertions checking. Clang Static Analyzer, Coverty, SonarQube, Clockwork, and PC Lint. Coding Standard 7, Exceptions. This little code snippet fails to handle exceptions properly, leading to potential crashes and undefined behavior. You can see that this code simply allocates a new integer array of 100 instances and then you delete it afterwards. What if the new resource allocation comes back failed and the ARR, the variable, the integer array is null, and then you delete that as a null pointer, or even you use it for processing? That is not robust at all. So to handle exceptions properly is to ensure resource deallocation and prevent crashes. First of all, you ensure that any dynamically allocated resources get deallocated, and also you want to make sure that when you allocate something, it is indeed successful before using that resource. So here we put first of all, we're using smart pointers, which is good. 2 things to note here, the use of try-catch block and use of smart pointers. Using smart pointers means you don't need to deallocate the integer array after use. So this after allocation goes out of scope, it will automatically deallocate the resources, so you don't have to worry about it. The try-catch block makes sure that if there are exceptions, it will catch it, and then you'll be notified of it. The users will be notified of it. So this is a much better, much robust version of doing something. Severity is high. Medium is likelihood medium, remediation cost medium, priority high, and threat level is 1. The 4 tools that can detect that you're doing correct exception handling is PVC Studio, Cover T, SonarQube, and Clockwork. Number 8, use of constants. So this is really, everybody should know about it already, but you need to be listed carefully on the policies and guidelines, because we're not talking about all the developers are seasoned developers. We may have interns. We may have some developers who are just starting out. Regardless, we need something to be observed and adhered to across the board. So this use of constants is referring to use of magic numbers directly in the code, meaning we don't want to hard code numbers in the code. People cannot make ends and tails out of a hard-coded number. What is it, right? And it makes it hard to understand and maintain. For example, here you are calculating an area. Length times 3.14, we know that's pi, but not everybody knows it, and not a good way to do it. 3.14 times radius times radius. So the magic number 3.14 can easily substitute it by a const, a double, give it a variable name pi, 3.14159, and then use it in this algorithm or in this arithmetic equation. Length times pi times radius is, in this instance, and that happens to be, the arithmetic that we want to do, and it's much more readable. Severity low, likelihood high, remediation cost low, priority medium, and level 3. We have several tools that you can automate this to check that you do not have magic numbers and you are using constant correctly. CPP check, SonarQube, Cover T, Clockwork, and PC Lint. All right, number 9. Very quickly, we need to initialize all variables. Like this very simple 2 lines of code, it did not initialize a variable and it could lead to possible undefined behavior. Right? X, what is X? It could have some special characters. It could have a gigantic number, and then you put it out to see out, and it could cause undefined behavior. Very easily plopped is that initialize X to some value, 0. Then you know I will be seeing 0, right? So this is much more robust, very simple. This is level 2 threat level. For automation tool, GCC can help you detect all the variables that you have not uninitialized and need to be initialized. Clang Static Analyzer, Cover T, PCV Studio, Clockwork, and CPP Check all can do this kind of checks. Last one is to avoid allocation in loops. Now look at this non-compliant version. This code allocates memory in a loop, leading to performance issues. Within the for loop, you are allocating a integer array of 1,000 instances. You do some processing with it and you delete this. And you do this, 100 instances, and you do this 1,000 times. This is going to slow down your program considerably. A better way to do it is very simple. You know it already. This code allocates memory outside of the loop, and this could improve performance in a dramatic way because you are not keep allocating resources and deleting it for 1,000 times. You simply just allocate this array with 100 instances, you do some processing, you can clean it up within the for loop, and then you delete this resource outside of the for loop, and that would improve your performance. Now, these little things could escape us easily if we're talking about thousands of lines of code, and we don't know where it slows things down. Now, usually within a for loop, you have maybe 100 lines of code to do something else, and you easily forget, oh, I'm doing allocation right within a for loop or a while loop, and that's causing the slowness. Don't do this. It pays to slow down and make sure that you are not doing this kind of allocation within a loop. This is a level 3 threat level. Automation tools that can help detect memory allocation in loops. It will tell you that you're doing this, and then you replace it with a better version that it will give you suggestions. Valgrind, Cover-T, Clockwork, PCB Studio, and PCLint, they all do this for you. All right, we are nearing the end. Before we end this segment, I would like to just point out, for automation tools, there are 3 different kinds. The static analysis tools for you are really focused on when you are doing compilation, when you're linking things before you actually deploy the code. So Cover-T, CPP Check, and Clang Static Analyzer does static analysis for you on your code. Dynamic analysis like Valgrind and Address Analyzer, these tools always runs at runtime. So at runtime, it will tell you something has gone wrong. You better go back and recheck. And then there are tools that will help you to automate things, and you can put it in your CI/CD pipeline. SonarQube is a continuously inspection tool for code quality and security. You put it in your CI/CD pipeline, and it does it every time when your code base is being touched. GitHub Actions, of course, GitHub. You could integrate your CI/CD pipeline right there, and then there are various actions you can carry on to make sure that every time your code base, your code repository is touched, this is being triggered and kicked off to do what it needs to do. All right, this is the end of part 2 of this presentation. Thank you for your audience, and please move on to part 3 and part 4 to complete this topic. Goodbye.